Experimental and FE investigations on the influential parameters in positioning and measurement of strain gauges in adhesively bonded single lap joints. Hello everybody, my name is Sadeghi. I'm a research assistant in Institute of Structural Mechanics and Lightweight Design, RWTH Aachen University in Germany. This work was accomplished with the collaboration of the other institute in Aachen, Welding and Joining Institute. Before we talk about the main topic that we want to present today, I would like to start with motivation, the challenges of advanced lightweight design. Basically, in the lightweight design, uncertainty drives weight. The uncertainty is coming from basically different sources: conservative load assumptions and safety factors, uncertain knowledge of fatigue lifetime, and also conservative allowable strain. In addition to these uncertainties, also costs are really important. Conservative assumptions of allowable damages, regular inspections that we would like to implement in the lightweight design, all creates costs. The other motivation, which is somehow related to our present work, is adhesively bonded joints in lightweight design. Basically, lightweight design is targeting to achieve three different goals: minimizing weight by the material which is used, material substitution, for example, sheet metals to composites, and also hybrid joints. Therefore, as a result, huge demand of adhesive in lightweight design is needed. And as a consequence, monitoring the structural integrity of such bonded joints is very vital. The concept of damage monitoring that we want to implement in the present work, Smart SHM. A Smart SHM approach. In the Smart SHM method, the healthy state of the structure is considered as a reference, and the properties of the structure with damage is compared with the reference state. So if we consider a single lap joint, the stress state on the single lap joint creates such a strain variation on the adherent over the bonded area, in which there is always a point with zero strain value. If we consider the strain variation again over the bonded area, so we can easily detect this zero strain point. This zero strain point is not dependent on the applied load as long as the damage is not occurred in the structure. Once the damage has occurred in the structure, the former zero strain point gets some value, and basically the comparison between the undamaged step and damaged step can create a structural damage indicator. So this concept was successfully implemented in adhesively bonded single lap joint with Araldit 2015 previously, which showed a very high potential for damage indicator in a case that a single lap joint is prone with different damage lengths. But how to implement the damage monitoring concept that we just explained? So let's talk about experiments and FE modeling that we carried out in the present. The experimental setup shows in the present slide, as you can see, that the geometry of the single lap joint is shown here. The material which was chosen for the adherent was a steel SC700MC with a thickness of 3 mm and a structural adhesive 3M-DP490, which is basically a two-component epoxy-based adhesive with a thickness of 0.7 mm was considered in the single lap joints tested here. So the tensile test was monitored with DIC system in order to record the local deformation of the joint over the tensile test. Also, for any individual test which was carried out in the present work, two strain gauges from both sides of the single lap joint was mounted, and the location of the strain gauges was basically determined with the help of FE analysis, which is exactly the same point that we previously discussed, the point with zero strain values. Material parameters and modeling techniques. As you can see, the table shows the material property that was given from 3M company for DP490. And for FE technique, traction separation law was basically chosen based on surface-based cohesive model. The damage initiation criteria was quadratic, and damage evolution criterion was Pavlov with the power of 1. As you can see, different FE modeling technique was chosen, basically was developed. First of all, a 3D symmetric model was developed, and also meanwhile a 2D approach in two different forms, plane stress and plane strain, were also considered. So contact between the adhesive and the adherent was modeled basically with the help of traction separation law, and the mesh size over the bond line area was 0.2 multiplied to 0.2 millimeter. So let's talk about the results. Deformation of the single lap joint using 3D FE symmetric model is shown in this picture. As you can see, that the state of the deformation is shown in a way that the damage is basically propagated from both sides of the single lap joint. As you can see the crack from both sides, which is completely propagated. On the other hand of the slide, you can see that the comparison of the load displacement between two experimental results and 3 FE models which was developed in the present work. The comparison between the experimental results and FE models shows a very good agreement. Since we had to mount the strain gauges on the location of zero strain points, so the longitudinal strain over the overlap lengths was also developed. As you can see that overall between the 2D and 3D model, the longitudinal strain shows more or less the same values, but as you can see for the 3D, the model is somehow shifted towards the right, and the location shows a bit different, which was basically expected because the strain on the width direction is not expected to be constant for the single lap joint. The longitudinal strain over displacement for the single lap joint tested and also FE analysis is shown in this slide. The comparison of FE and experimental showed interesting results. As you can see, the FE results always show much lower values of strain compared with experiments. This is surprising since the previous FE results showed a good agreement for predicting low displacement curves. Apart from that, you can see that even for experimental results, one cannot see a general good agreement. In addition to that, you can see, for example, for any individual experimental test, if you, for example, consider experimental 1, there is not a same trend for a strain gauge which is mounted on the front side and the back side of the single lap joint. So due to different reasons that we can consider it later, this can be a normal behavior in single lap joint, that the crack does not start at the same time from both ends of the single lap joint, and that's why we don't expect a symmetric crack propagation and consequently the similar strain variation for front and back side of the single lap joint, as we expect in our FE analysis, which is basically a symmetric crack propagation. So in this slide, longitudinal strain over normalized load is illustrated. As you can see, more or less the same trend can be observed with the previous slide. Almost there is not a general good agreement between FE predictions and also experimental results. So, but what could be the possible answers for such a discrepancy between the experimental and FE analysis? In spite of the fact that the FE analysis was able basically to predict the failure load in a very good and accurate level. So one of the possible reasons that could lead to such a discrepancy is the strain misalignment. But what is the influence, or how big is the influence of strain misalignment on the strain which is recorded by strain gauges? So as you can see here, the strain variation for different strain misalignment is shown here, from 1 millimeter to 3 millimeter from both sides, from right side of the 0-point strain and also from left side of the 0-point strain is shown here with the help of the FE analysis. And as you can see, it's compared with the reference model, which is the FE model. Here in this slide, you can see that the very even small strain misalignment can lead to very big changes in the strain which is recorded in the strain gauges. So if we compare the experimental results, so you see that simply lies in the upper and lower band of the analysis that we implemented here, up to 3 millimeter misalignment in the strain gauge installation. Apart from that, making a perfect joint is almost impossible, and there are always tolerances in the assembly process, such as adhesive thickness tolerance, overlap tolerance, and also when we do the test, it could be temperature variation. So with these basically geometrical tolerances, so we wanted to investigate the interaction of such a tolerance using DOE, or design of experiment method. So basically we were aiming to define upper and lower band for strain measurements in order to investigate the dependence of a structural damage indicator, or SDI, on the geometrical tolerances, and also it could be later developed for temperature variation. Therefore, with the help of DOE technique, combined effects with a strain gauge misalignment in contribution with geometric tolerances was investigated, and as you can see that an upper and lower band was achieved for the strain measurement prediction of such a joint. So the upper and lower band achieved by the help of DOE based on interaction of geometrical tolerances, which is available in the assembly process of the single lap joint, also mounting the strain gauge on the joint, is compared with the experimental result. It shows that always experimental basically lies lower than the developed band lines. As for the conclusions, a method was implemented for monitoring the damage detection in adhesively bonded single lap joint in this work. The method works based on monitoring the strain on the point with initial zero strain value. Once the damage is initiated on the joint, the former zero strain point shows some values. They implemented a FE model for modeling the fracture behavior of single lap joint based on the traction separation law was successful. The strain measured by strain gauges was proved to be highly influenced by the geometrical tolerances. By considering the coupled effect of geometrical tolerances in the joint and temperature variation, a relation can be developed for the structural damage indicator in subjoints. I would like to thank also the Federal Ministry of Economic Affairs and Energy of Germany for the financial support through the Research Association DESHEMA for the projects that we were basically working on it, and also 3M Germany GmbH for providing adhesive DP490. Thank you for your kind attention.